Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to imagine just for a second that you're standing outside on a clear, dark night in the southern hemisphere.
Right, away from all the city lights, hopefully.
Yeah, exactly. Way out in the middle of nowhere. You look up, away from the familiar constellations you might know, and your eyes catch this fuzzy, bright patch of light in the sky.
Which, pretty noticeable even to the naked eye.
It is. And for centuries, basically anyone who looked at it just assumed it was a star. You know, just a single, maybe slightly smudged star.
Yeah, a bit out of focus, maybe.
Right, but if you were to take a powerful telescope and actually zoom in on that one little patch, you wouldn't find a star at all. You'd find this chaotic, impossibly dense swarm of roughly 10 million stars, all bound together by gravity.
The sheer scale of that visual shift is just profound. I mean,
Yeah.
what registers to your eye as a solitary point of light is in reality this sprawling metropolis of stars.
It's
It
wild.
really is. It forces a complete recalibration of how you perceive the night sky, you know?
And today, we're heading right into the heart of that metropolis. We are exploring a historic astronomical breakthrough from July 2026, which is the discovery of an object known as oMEGACat BH2.
A very kitschy name.
Oh, astronomers are the best at naming things, right? But this is actually the very first confirmed stellar mass black hole inside that massive stellar swarm, which is called Omega Centauri.
Yeah, and the hunt for this particular object represents, honestly, one of the most complex detective stories in modern astrophysics.
Oh, absolutely.
Because it required astronomers to completely abandon their traditional methods of finding black holes. And they basically had to invent an entirely new, incredibly patient way of analyzing the universe.
So the mission for our conversation today is to really figure out the mechanics of that detective work. We're going to explore how astronomers finally managed to find an invisible object that had just been hiding in plain sight for decades.
Hiding very quietly, too.
Exactly. And more importantly, we're going to break down how this single, very quiet discovery fundamentally rewrites the physics of how galaxies evolve, how stars interact, and really how black holes themselves even come to be.
Because finding a black hole that isn't actively consuming matter, one that's just sitting there in the dark, it requires an understanding of orbital dynamics and data analysis that basically borders on the extreme.
Right. But to understand the weight of that achievement, we really have to start by setting the scene, I think.
Yeah. Let's look at the crime scene.
The cosmic crime scene. Omega Centauri, or NGC 5139 if you prefer the catalog name. Let's paint the picture of this environment because it honestly defies common sense.
It really does.
So this object is located about 18,000 light years away from us. It contains roughly 10 million stars, which translates to somewhere between, 3.6 to 4 million times the mass of our own sun?
Yeah, that's the current estimate. It's incredibly heavy.
But all of that mass is packed into a spherical area just 150 light years across.
Which is mind-boggling. Just to put that 150 light-year diameter into perspective, the closest star system to our sun is Alpha Centauri.
Right, which is about 4 light years away.
Exactly. So in our stellar neighborhood, space is mostly just that it's empty space. But in the core of Omega Centauri, the average distance between stars is a tiny fraction of a light year.
I was actually trying to wrap my head around that density, and I came up with this analogy. It's basically like taking the entire population of New York City.
Booth is a good one.
Yeah, all 8 million people, and forcing them to live, work, and just exist entirely inside the borders of a single tiny rural village.
It's just absolute crowding.
Yeah, the crowding is just absolute.
And that visual works on a gravitational level, too. The sheer proximity of the stellar neighbors basically dictates the physics of the entire region. I mean, if Earth were somehow relocated into the core of Omega Centauri, our night sky wouldn't even be dark.
Wait, really? It would just be daylight?
Well, not daylight, but it would be blazing with thousands of stars that appear brighter than Venus does to us now. The ambient light would be so intense you could likely read a book by starlight alone.
Oh, wow.
Yeah, you'd be casting distinct shadows at midnight.
Which sounds super poetic, but when you think about the gravitational reality of that, it would be absolute
Yeah.
chaos, just millions of massive objects constantly pulling on each other.
Exact.
And yet, the density isn't even the weirdest part about Omega Centauri, is it? Because it stands out from basically every other star cluster in the Milky Way for a totally different reason.
Yeah, what's fascinating here is the anomaly in its chemical and kinematic complexity.
Okay, unpack that for me.
Sure. So to understand why Omega Centauri breaks the rules, we first need to look at what a standard globular cluster is supposed to be. In astrophysics, a normal globular cluster is considered a simple stellar population.
Meaning they're all kind of the same.
Right. The prevailing theory is that all the stars in a standard cluster formed in a single massive burst of star formation, all from the exact same giant cloud of molecular gas.
Oh, I see. So they're basically like a graduating class of stars. They were all born at the exact same time from the exact same material.
That's a perfect way to put it. Therefore, they share the same age and the same basic chemical composition. When we look at their light spectra, the signatures of elements like iron or oxygen, they're largely uniform across the whole cluster.
And because they all baked in the same oven.
Exactly. But when astronomers apply that same spectroscopic analysis to Omega Centauri, the data is just completely fractured.
It doesn't match.
Not at all. We see multiple distinct populations of stars in there. They have completely different ages, and their chemical makeups vary wildly.
Huh.
And furthermore, they don't even move together in a simple uniform orbit. The kinematics, the actual physical motion of the stars, shows distinct groups moving in completely different ways.
So if it doesn't look or act like a normal uniform cluster, the obvious deduction is that it didn't form like one, right?
Right.
So what is the alternative mechanism? Like, what creates a massive chaotic ball of stars with all these different ages and chemicals?
Well, the leading theory, and really the only one that successfully accounts for this bizarre data, is that Omega Centauri is not actually a true globular cluster at all.
Wait, really? Then what is it?
The overwhelming consensus now is that it's the stripped remnant core of an ancient dwarf galaxy.
Oh, wow. Meaning it used to be a completely independent galaxy just floating out in the universe, totally separate from the Milky Way.
Exactly. Billions of years ago, this dwarf galaxy ventured a little too close to the Milky Way, and our galaxy is, vastly more massive. So its immense gravity just went to work.
It bullied the smaller galaxy.
Yeah. Through a process called tidal stripping, the Milky Way essentially cannibalized it. The gravitational tides literally ripped away all the outer layers of stars, all the loose gas, the dust.
I've peeled it like an onion.
Right. Stretched them out into these long streams and pulled them into our galaxy's own halo.
So the Milky Way basically ate the outer layers, and Omega Centauri is just the dense pit left over after the peach was devoured.
A very massive,
Yeah.
extremely old pit, yes. We are looking at a core that is roughly 12 billion years old.
12 billion. That is, the universe itself is only about 13.8 billion years old, right?
Exactly. So it's ancient.
Yeah.
And because of this extreme age and this intense gravitational crowding, Omega Centauri serves as this perfect natural laboratory. It allows us to observe stellar evolution pushed to its absolute limits.
Because we're seeing the end game.
Right. We can see what happens when stars are forced to live out their entire life cycles from birth to death in an environment where they are just constantly interacting with their neighbors.
Which sets up the central mystery of this entire deep dive. Because of that 12 billion year age and the sheer number of massive stars that must have existed there, physicists looked at Omega Centauri and realized it should be an absolute graveyard of massive dead stars.
It absolutely should be. The absence of those dead stars was one of the most glaring discrepancies in stellar astrophysics for decades.
The math didn't match the reality.
Not even close. The observational data fundamentally contradicted the established mathematical models.
And this became known as the Great Black Hole Drought of Omega Centauri.
The drought, yes.
So let's break down the mechanics of this drought, because the physics of stellar death basically guarantees they should be there, right? Like, we know that the most massive stars burn through their nuclear fuel incredibly fast.
Live fast, die young.
Right. They live for maybe a few million years, exhaust their energy, and die in these massive supernova explosions. And the crushed cores they leave behind become stellar mass black holes.
Yeah. These are black holes with masses ranging from a few times that of our sun to perhaps a few tens of solar masses. And when you take a starting population of 10 million stars and you let the clock run for 12 billion years.
That's a lot of supernovas.
A huge amount. You can actually calculate what we call the initial mass function, which is basically the statistical distribution of how many stars of each size were born in that cluster.
And what did the models say?
The computer models were completely unambiguous. They calculated that roughly 10,000 stellar mass black holes should be left over.
10,000 just lurking inside this one cluster.
10,000 black holes.
Huh.
And the models actually went further than just predicting their existence, too. They predicted their exact location.
Because they wouldn't just stay where they died, right?
Exactly. In a dense environment like a globular cluster, objects don't just stay where they're born. They're subject to a process known as dynamical friction.
Okay, I want to pause on dynamical friction for a second because friction in the vacuum of space sounds totally counterintuitive.
Yeah, it does sound a bit weird, yeah.
Like there's no air, there's no physical surface to rub against. How does a black hole experience friction?
Well, the term is slightly metaphorical, but the physical effect is identical to friction. It's entirely gravitational. Picture a very heavy object like one of these stellar mass black holes, and it's moving through a dense sea of much lighter objects, which would be the normal main sequence stars.
Right.
As the black hole moves, its strong gravity pulls slightly on all the lighter stars it passes by.
Oh, so it alters their trajectories, pulling them inward toward its own path.
Exactly. And as those lighter stars are pulled inward, they form a region of higher density behind the black hole. It's effectively a gravitational wake, much like the wake a boat leaves as it moves through water.
Okay, that makes sense. And that wake of clustered stars obviously has mass, which means it has a collective gravitational pull of its own.
You've got it. So that backward pull from the wake actually saps the black hole's kinetic energy.
So the black hole creates a cluster of stars behind it, and then the gravity of that cluster pulls backward on the black hole itself, slowing it down.
Yes, it loses momentum. And in the orbital mechanics of a star cluster, when a massive object loses kinetic energy, its orbit shrinks. It essentially falls deeper into the gravitational well.
It sinks toward the very center of the cluster.
Precisely. And because of the conservation of energy, the lighter stars that made up that wake, they must be gaining the kinetic energy that the black hole lost.
Oh, so they get pushed outward.
Right. The heavy objects sink to the core, and the lighter objects puff outward. When you apply this process of dynamical friction over a span of 12 billion years, the physics dictates that virtually all of those 10,000 predicted black holes should have plummeted straight into the densely packed core of Omega Centauri.
Okay, but if I'm an astronomer looking at this model, I immediately see a massive logical problem.
Which is?
Well, if you take 10,000 black holes and you force them all to sink into the exact same tiny, crowded central core, shouldn't they be causing absolute havoc?
You would think so.
Right. Like, they should be colliding with each other, gobbling up all the normal stars that are packed in there, and setting off these massive, bright flares of radiation that we can easily see from Earth. How do you just lose 10,000 black holes in a crowded room?
It's a great question. But the assumption that they should be setting off flares is exactly where traditional observation hits its limit. To really understand the drought, we have to examine the limitations of our own technology.
Because we don't actually see black holes.
Exactly. We don't see them. We detect the radiation generated by the material they are actively consuming.
Right, the classic accretion disk model. The black hole's gravity pulls in gas from a nearby companion star or maybe a passing cloud.
Yes.
And then that gas swirls around the black hole, accelerating to a significant fraction of the speed of light. The friction within that swirling gas superheats it to millions of degrees, causing it to blast out high-energy X-rays or radio waves right before it crosses the event horizon.
And that mechanism is how we confirm the existence of early candidates, like Cygnus X1, for example.
Right.
But the generation of those X-rays is entirely dependent on an active, plentiful food supply. The black hole literally needs loose interstellar gas or a companion star positioned perfectly to be siphoned.
And you're saying Omega Centauri is lacking that food supply?
It is entirely barren of loose gas.
How is that possible with 10 million stars?
Well, consider the history of the cluster. Over the first few 100 million years of its 12 billion year life, thousands of massive stars went supernova.
Right, the early fast-burning ones.
Exactly. And the sheer kinetic force of those explosions, combined with the intense radiation pressure from millions of other stars, it all acted as a giant cosmic broom.
Oh. So the energy blasted all the loose gas and dust completely out of the cluster's gravitational hold.
Billions of years ago, yeah. The pantry was swept completely clean. Therefore, the vast majority of these black holes have absolutely nothing to consume.
And a starving black hole is a silent black hole.
Perfectly silent. Without an accretion disk generating X-rays, it is just a completely dark sphere of extreme gravity sitting against the black backdrop of space. X-ray observatories could stare at the core of Omega Centauri for years and see basically nothing but the faint signatures of a few normal stellar binaries.
Okay, that perfectly explains the lack of X-rays. But X-rays aren't the only tool in the astronomer's box, right? What about radial velocity?
Ah, radial velocity.
Because that's the technique astronomers use to find exoplanets all the time. You look for the physical wobble of a star. Like, if a visible star is orbiting an invisible black hole, the gravity of the black hole will yank the star in a circle.
Correct.
So from Earth, we would see the star being pulled slightly toward us and then pushed slightly away from us.
A Doppler shift. As the star moves toward us, its light waves get compressed, shifting toward the blue end of the spectrum. And as it moves away, the waves stretch out, shifting toward the red end.
Exactly. So why didn't astronomers just look for stars in the core of Omega Centauri that were shifting red and blue? The black holes might be invisible, but their gravity would be throwing the visible stars around like rag dolls.
Well, the physics of the Doppler shift works perfectly. But the application of radial velocity requires an environment that Omega Centauri simply refuses to provide.
It's too crowded.
It's way too crowded. To measure that subtle red and blue shift, an astronomer must capture the light from one single, specific star and feed it into a spectrograph.
Right, the prism that breaks the light apart.
Yes. The spectrograph spreads the light out into a rainbow, revealing the dark absorption lines created by elements in the star's atmosphere. And the shifting of those lines is what tells you the velocity.
So you have to strictly isolate the light.
And in the core of Omega Centauri, isolating light is nearly impossible. The crowding is so severe that the light from thousands of faint stars just bleeds together on our telescope sensors.
It all just washes out.
It creates a blended wall of illumination. If you try to take a spectrum, you're getting the mashed up light of 50 different stars at once. You just cannot isolate the absorption lines of one specific star well enough to measure the tiny, subtle wobble caused by a quiescent black hole.
Wow. So traditional astronomy basically hit a brick wall. The mathematical models demanded the black holes be there, but the two primary methods of finding them were completely useless.
Yeah, X-rays failed because there was no gas to eat, and radial velocity failed because the cluster was just a blinding wall of blended light.
The ghosts were hiding in the noise.
That's a very poetic way to say it, but yes,
Right.
Overcoming that barrier required a fundamental shift in strategy. Instead of looking for radiation or looking for the shifting color of light, astronomers had to invent a completely different game of cosmic hide-and-seek.
And they turned to a technique that requires, frankly, an almost unfathomable level of patience, data management, and precision.
Absolute precision.
Which takes us to the actual detective work. Jumping ahead to July 2026, a team of researchers led by Matthew Whitaker at the University of Utah finally cracked the case.
Yes, they bypassed X-rays and radial velocity entirely and utilized a technique called high-precision astrometry.
Okay, let's unpack this. What exactly is astrometry?
Astrometry is, historically speaking, the oldest branch of astronomy. At its core, it's the painstaking measurement of a star's physical geometric position on the sky and then tracking how that position changes over time.
Okay, so the distinction here is crucial. Radial velocity measures how a star moves toward or away from us along our line of sight by analyzing the color of light. Astrometry completely ignores the color.
Exactly, it ignores the spectrum.
It's measuring how a star moves side to side, vertically and horizontally across the two-dimensional canvas of the sky.
Yes, astronomers refer to this side-to-side movement as proper motion. Every star in Omega Centauri is in motion, naturally orbiting the center of mass of the cluster. So if you watch a star over a long enough period, you can just map its trajectory.
But the distances we're talking about make this sound technologically impossible. Like, Omega Centauri is 18,000 light-years away. A star moving side to side at that distance trying to track that from Earth.
It's incredibly difficult.
It sounds like trying to track the physical flight path of a single specific firefly in the middle of a blinding blizzard from hundreds of miles away, just to see if its flight path is being pulled slightly off course by an invisible string.
That is a very accurate analogy. The scale is completely daunting. From our perspective on Earth, the physical movement of a star in Omega Centauri across the sky is microscopically small. We measure this movement in fractions of a milliarc second.
Which means nothing to most people. What does that translate to on a telescope?
To translate that into the actual equipment used, we are talking about tracking subpixel movements on a digital camera sensor.
Let's define what subpixel movement actually means, because a digital sensor is made of a grid of tiny squares, the pixels. You're saying the star's movement across the sky is so small that the point of light doesn't even cross from one pixel to the next.
It moves significantly less than the width of a single digital pixel.
That's crazy. How do you even measure that?
Well, when a telescope captures a star, the light doesn't just illuminate one square perfectly. It spreads out over a tiny cluster of adjacent pixels in this bell curve shape, which we call the point spread function. So by analyzing the exact intensity of light hitting each individual pixel in that cluster, advanced mathematical algorithms can calculate the precise geometric center of that blob of light to a fraction of a single pixel.
But doing that once doesn't tell you anything about movement. You have to do that over and over again to see if the center of the blob is shifting.
Right, you need a long temporal baseline to confidently detect a subpixel wobble. You can't just take a picture and then look at it a while later. You need to watch that specific star for years or even decades, constantly calculating the center of its light profile and plotting it on a graph to see the microscopic path it traces over time.
Which perfectly explains why the Hubble Space Telescope was the crucial tool for this discovery.
Absolutely. Hubble provided the two mandatory ingredients for high-precision astrometry: extreme clarity and a vast archive of time.
Right, because it's in space.
Exactly. Because Hubble orbits above the blurring, turbulent effects of Earth's atmosphere, its angular resolution, its ability to distinguish fine details is just exquisite.
The atmosphere doesn't smear the light, so that point spread function you mentioned is incredibly sharp.
Yes. And just as importantly, Hubble was launched in 1990. So it's been operational and staring at the sky for a very long time. Bobby Whitaker's team didn't ask for new telescope time. They just went into the archives.
They dug through the old hard drives.
They retrieved over 20 years of historical photographs that Hubble had taken of Omega Centauri.
So they laid 2 decades of images on top of each other and ran those subpixel tracking algorithms on thousands of individual stars.
They were basically looking for a star that was moving incorrectly. Because if a normal star is just moving through the gravitational field of the cluster on its own, its proper motion across the sky should trace a relatively smooth straight line or maybe a gentle arc.
Okay.
But if a star is locked in an orbit with a massive invisible companion, the gravity of that companion will constantly yank it off that straight path.
As the whole system moves forward, the visible star is spinning around the invisible center of mass. So instead of a straight line, it traces like a little corkscrew or a wavy line across the sky.
Exactly. The technical term is an astrometric wobble. And out of the millions of stars in the cluster and the thousands they analyzed with this extreme precision, the team found one specific star that exhibited an undeniable wobble.
Just one.
Well, the most obvious one. It's a main sequence star, meaning it's still actively fusing hydrogen into helium, and it has roughly 78% the mass of our own sun.
So just a completely normal, healthy star, but the 20-year archive showed it was carving this curved orbital path. It was being yanked back and forth by something incredibly heavy, yet completely dark.
The astrometric data from Hubble was revolutionary, but it wasn't the absolute end of the process.
Why not? Didn't they have the wobble?
They did, but even with the clarity of space, the very core of Omega Centauri is so packed that the visible light from neighboring stars can occasionally overlap the target star.
Oh, right, the crowding again.
Yeah, that overlap subtly distorts the shape of the point spread function, which introduces a tiny margin of error into the orbital calculations.
So they knew the wobble was there, but the crowding made it hard to measure the exact shape of the orbit with total certainty. They needed to basically clean up the image.
Precisely. To refine the measurements to the point of undeniable proof, they required a telescope that could literally ignore the crowding. They needed the James Webb Space Telescope.
Okay, this is where the engineering becomes really elegant, because Webb isn't an optical telescope like Hubble. It doesn't see visible light. It's optimized for infrared light. Why does looking in the infrared solve the problem of crowding?
It comes down to wavelengths. Visible light has relatively short wavelengths. When visible light encounters cosmic dust or passes through an intensely crowded field of stellar emissions, the short waves scatter and bleed into each other.
Which creates that blended wall of light we discussed earlier.
Exactly. Infrared light, however, operates at much longer wavelengths.
So the longer waves can literally just step over the tiny dust particles and cut through all the interference.
That's a great way to visualize it. The infrared radiation penetrates the visual noise. Webb's unparalleled infrared sensitivity, combined with its massive mirror, allowed it to pierce straight through the crowded visible light field of Omega Centauri.
Wow.
It cleanly separated the target star from its brilliant neighbors, nailing down its exact geometric position with absolute clarity.
So the workflow is basically this. Hubble does all the heavy lifting, providing the 20-year historical baseline to prove the star is definitely wobbling. And then Webb comes in at the end with this hyper-precise infrared sniper shot to confirm exactly where the star is at this current moment, locking down the orbital parameters once and for all.
Exactly. The combination of long baseline optical archives and cutting-edge infrared precision is what finally revealed the exact shape and duration of the orbit.
So this 20-year staring contest finally yielded a result. They found the anomaly. Let's officially introduce the object they discovered.
The invisible companion was designated oMEGACat BH2.
BH2, so it's the second candidate.
It is the second black hole candidate identified in the cluster by the broader oMEGACat survey, yes.
Huh.
But it holds the distinction of being the very first to be definitively confirmed as a stellar mass black hole.
Let's dig into the specific physical properties of this invisible heavyweight, because the numbers themselves actually create a whole new set of scientific problems.
They really do.
So the astrometric data, how hard the visible star was being yanked around, allowed the team to calculate the mass of the invisible companion. The consensus is that oMEGACat BH2 has a mass of approximately 4.46 times the mass of our sun.
Very specific number.
Very specific. But before we discuss why that number is so strange, there's a fundamental physics question that needs to be answered here. We have an object that weighs 4.5 solar masses. We know it emits absolutely no light. But how can astrophysicists definitively state that it's a black hole? Could it not just be a massive dead star, a really heavy neutron star that has just gone cold?
It's a valid question. The ruling out of a neutron star relies on the absolute limits of nuclear physics.
Okay, lay it on me.
So, a neutron star is the crushed core of a massive star that has gone supernova. It's incredibly dense. A teaspoon of neutron star material would weigh billions of tons. But crucially, it is still made of physical matter.
Right, it has a surface.
Yes. It's a sphere of neutrons packed as tightly together as the laws of quantum mechanics will allow.
So the neutrons are physically resisting being crushed any further.
Exactly. The phenomenon is called neutron degeneracy pressure. It stems from the Pauli exclusion principle, which basically dictates that two fermions, in this case neutrons, cannot occupy the exact same quantum state simultaneously.
They refuse to share the same space.
Right. And this creates a powerful outward quantum pressure that fights against the inward crush of gravity.
But matter has a breaking point, right? Gravity is relentless. If you keep adding mass to that neutron star, eventually gravity has to win.
It does. There is a strict theoretical upper limit for how massive a neutron star can be before that quantum pressure simply fails. Gravity completely overpowers the structural integrity of the neutrons, and the object collapses entirely in on itself, shrinking down to an infinitely dense point, a singularity, a black hole.
What is that magic number? Where does the neutron pressure fail?
Well, based on our most advanced understanding of nuclear physics and equations of state, that absolute upper mass limit for a neutron star, known as the Tolman-Oppenheimer-Volkoff limit, is roughly 2.1 to, at the very maximum, 2.5 solar masses.
Okay, so if an object is heavier than 2.5 solar masses and hasn't blown itself apart, it literally must collapse into a black hole.
Yes. And oMEGACat BH2 comes in at 4.46 solar masses.
Which is way over the limit.
The calculations are definitive. Even when factoring in the most conservative modeling assumptions and the widest margins of error, the formal mass range for this object is calculated to be between 3.45 and 5.68 solar masses.
So even if the measurements are off and it sits at the absolute lowest end of the margin of error, 3.45 solar masses, it's still a full solar mass heavier than the absolute breaking point of a neutron star.
Exactly. It's decisively above the limit. When physics dictates an object is that massive and observations confirm it emits no light whatsoever, there's only one mathematically sound conclusion. It is a black hole.
So the identification is locked. It is a 4.5 solar mass black hole. But this is where the discovery stops being just a neat detection and starts actively breaking the established models of stellar evolution.
Oh, it really throws a wrench in the works.
Because to an average person, 4.5 times the mass of the sun sounds enormous. But to an astrophysicist, this black hole is actually considered shockingly, anomalously tiny.
The mass is remarkably low, and the reason it's considered so low highlights a major complication in our understanding of a property called metallicity.
Okay, we definitely need to define metallicity clearly, because astronomers use the word differently than chemists do.
Yes, we do.
In astronomy, metal doesn't just mean iron, copper, or titanium.
Correct. In the context of astrophysics, hydrogen and helium are the fundamental building blocks of the universe, created during the Big Bang. Literally every other element on the periodic table, carbon, oxygen, nitrogen, iron, is considered a metal.
It's just a catch-all term for the heavier stuff.
Exactly. These heavier elements are forged inside the cores of stars and then scattered across the universe when those stars die in supernovas.
So a younger star born recently will have a lot of metals in it because the universe has had billions of years to get polluted with all these heavy elements.
Right. But Omega Centauri is extremely old. It's roughly 12 billion years old. The stars inside it formed very early in the timeline of the universe, long before countless generations of supernovas could enrich the galactic environment with heavy elements.
So the stars in Omega Centauri have very low concentrations of these heavier elements.
Yes, it is an extremely metal-poor environment.
Okay, the environment is metal poor. But what does the lack of trace elements like carbon or oxygen have to do with the final size of a black hole?
The connection lies in the violent final stages of a massive star's life. When a massive star nears the end of its fusion cycle, it becomes highly unstable. The immense heat and radiation generated in the core push outward with incredible force.
Okay.
This creates what we call stellar winds, a process where the star physically blows its own outer layers of plasma out into space.
The star is essentially shedding mass, bleeding its own weight out into the vacuum before it dies.
Exactly. But the sheer force of those stellar winds is completely dependent on metallicity. The mechanism works through radiation pressure. In the core of the star, photons are generated, and they travel outward.
Right.
If the outer layers of the star contain a lot of metals, heavy elements with complex atomic structures and lots of electrons, those atoms are highly opaque to the radiation.
So the photons basically crash into the heavy atoms.
They crash into them, and the atoms absorb the photons. That absorption transfers the physical momentum of the photon to the atom. The intense radiation literally pushes the heavy atoms outward, driving a massive, powerful stellar wind that strips huge amounts of mass away from the star.
Wow, so a metal-rich star acts like a giant sail catching the wind of its own light, basically blowing its mass away.
That's a fantastic analogy. But if a star is metal poor, like the ancient stars in Omega Centauri, it's mostly just transparent hydrogen and helium. The outward-flowing photons simply slip right through the gas without hitting much.
The radiation pressure has nothing to push against.
Consequently, the stellar winds are incredibly weak.
The sail has holes in it.
Yes. The metal-poor star cannot effectively blow away its outer layers. It retains nearly all of its mass right up until the moment it runs out of fuel and the core collapses.
Oh, I see where this is going. Because it held onto its mass, when it finally goes supernova, there is vastly more physical material left over to collapse inward and feed the formation of the black hole.
Therefore, the theoretical models of stellar evolution confidently predicted that in a metal-poor environment like Omega Centauri, the resulting stellar mass black holes should be extraordinarily heavy. We're talking about black holes that are 20, 30, perhaps even 50 times the mass of the sun.
The math says metal-poor stars make giant black holes. And yet, oMEGACat BH2 is only 4.5 solar masses. It's puny.
It defies the predictive models entirely. The existence of a 4.5 solar mass black hole in such an ancient, metal-poor cluster challenges the fundamental physics of how we thought these stars lived and died. It implies that there must be other mechanisms at play that we haven't fully accounted for.
Like what? If radiation pressure didn't blow the mass away, what did?
Well, astrophysicists are now forced to reevaluate how other factors might strip mass from a dying star. For instance, extreme rotational velocity. If the star was spinning incredibly fast, centrifugal force might have thrown mass off the equator.
Oh, interesting.
Or complex binary interactions. If the progenitor star was originally part of a tight binary system, a companion star might have siphoned off its outer layers through gravitational stripping long before the core collapsed. We really thought we understood stellar death in the early universe, but this one anomaly demands a rewrite of the textbook.
It's incredible how a single microscopic wobble of light can just unravel decades of established theory.
It's what makes astrophysics so exciting.
But the low mass of oMEGACat BH2 is only half of the puzzle here. The physical mechanics of its orbit present a paradox that is arguably even more baffling than its weight.
The orbital timeline of this binary system completely contradicts the environment it exists in.
Let's lay out the data. The astrometric tracking from Hubble revealed that the visible main sequence star takes 94 years to complete one single orbit around the invisible black hole.
A 94-year orbital period is exceptionally long. In fact, it is the longest orbital period ever measured for any black hole binary system discovered to date.
Let's visualize what a 94-year orbit actually means in terms of physical space. According to Kepler's laws of planetary motion, if an orbit takes that long, the two objects cannot be close together. They must be moving very slowly, and they must be separated by a massive physical distance.
They are engaged in an extremely wide, loose orbit. The gravitational tether holding the star to the black hole is stretched across a vast distance. Because they're so far apart, there are no strong tidal forces ripping material from the star. It's a very quiet, distant, and relatively weak gravitational relationship.
Here's the visual that strikes me. A 94-year orbit is like two people holding hands and engaging in a very slow, very gentle waltz.
Okay, I like that.
But you have to remember the context of where this waltz is taking place. They are in the exact center of Omega Centauri. It's the equivalent of trying to maintain a slow, romantic dance in the dead center of a violent, chaotic, heavy metal mosh pit.
The mosh pit analogy captures the dynamical reality perfectly. In the dense core of Omega Centauri, the physical distance between stars is minimal, and their relative velocities are extremely high. Gravitational encounters are not rare events, they are constant.
Right.
Stars are continually zipping past one another, their gravitational fields tangling and violently transferring kinetic energy.
So the bodies in the mosh pit are constantly slamming into the two dancers.
Precisely. In the field of astrophysics, a wide binary system like oMEGACat BH2 is classified as a soft binary. It is incredibly fragile. The gravitational bond holding the 94-year orbit together is weak, simply because of the vast distance between the star and the black hole.
So what happens when another star gets close?
When a third, random star from the cluster zooms closely past them, its transient gravitational pull easily overpowers the weak tether holding the binary together.
It injects kinetic energy into the system, essentially snapping the tether and ripping the star and the black hole apart, sending them flying in opposite directions.
Yes. Dynamical supercomputer simulations of globular clusters map these interactions with very high fidelity. The simulations show unequivocally that a fragile, wide binary system with these specific properties, living in an environment with this extreme density of passing stars, should be disrupted and completely torn apart in less than 1 billion years.
Less than 1 billion years is the maximum survival time. But here is the inescapable logical collision. We established earlier that the Omega Centauri cluster is roughly 12 billion years old.
The age is well constrained.
Yes. But the laws of gravity and kinetic energy dictate that this fragile 94-year binary system would be annihilated in just 1 billion years. Therefore, this black hole and this star absolutely cannot be a primordial pairing.
Right.
They could not have formed together from the same gas cloud 12 billion years ago because they never would have survived the mosh pit this long.
The conclusion is inescapable. The system cannot have existed in its current state for the lifetime of the cluster. The fact that we are observing it right now, intact and orbiting, implies with absolute certainty that this binary system formed relatively recently.
But if they didn't form together, how did a perfectly normal main sequence star in a 4.5 solar mass black hole suddenly find themselves locked in a gentle 94-year waltz? They didn't just casually drift into each other's gravity, right?
No. The mechanics of capturing a companion in space require a way to bleed off excess kinetic energy. Two objects cannot just fly past each other and magically enter an orbit. They would just slingshot away.
Right.
To form a binary dynamically, you require chaotic multi-body physics, specifically 3-body and 4-body interactions. The core of a globular cluster is essentially a factory for these violent exchanges.
So they are actively playing musical chairs, swapping partners.
The process is incredibly violent. Imagine a single black hole soaring through the dense core. It happens to have a close, high-speed encounter with a pre-existing binary star system. Two normal stars that are already orbiting each other.
Okay.
As the massive black hole plunges into the system, its extreme gravity destabilizes the orbit of the two stars. The laws of physics demand that energy and momentum be conserved.
So the black hole acts like a wrecking ball.
Exactly. The gravitational interaction flings one of the normal stars completely out of the system, ejecting it into space at high speed. The kinetic energy required to eject that star is stolen from the overall system.
And because that energy is lost?
Because it's lost, the black hole is forced to slow down, and it essentially drops into the empty seat, capturing the remaining star into a new orbit.
Wow. The black hole literally stole a partner from an existing couple.
Or consider the reverse. A binary system that already consists of two black holes might interact with a passing main sequence star. The gravitational chaotic dance ejects one of the black holes, and the star is captured in its place. These interactions are constantly breaking apart old partnerships and forging new ones.
So the oMEGACat BH2 system is essentially a newly formed couple that met violently in the cosmic mosh pit.
Yes.
And humanity just happens to be looking at them right now during this brief 1 billion-year window before they inevitably encounter another rogue star and get torn apart again.
It's a fleeting configuration on a cosmic timescale. And this realization transcends mere trivia. The discovery of oMEGACat BH2 provides direct, undeniable observational evidence that these violent partner-swapping exchanges are actively occurring right now in the center of Omega Centauri.
It's not just theory anymore.
No, it shifts the entire concept of dynamical binary assembly from the realm of theoretical supercomputer simulations into observed, verifiable reality.
Which means this same game of violent musical chairs isn't just happening in Omega Centauri. It must be happening in the cores of globular clusters all across the universe.
Absolutely.
And that is the perfect pivot to discuss the larger implications. Why does this single, distant black hole matter to the broader field of physics? Why should someone listening care about an invisible object 18,000 light-years away? The answer connects this quiet discovery directly to the most energetic and violent events in the cosmos: gravitational waves.
The link is fundamental. For years now, massive Earth-based interferometers like LIGO and Virgo have been detecting gravitational waves, these literal ripples, stretching and squeezing the very fabric of space-time, traveling across the universe at the speed of light.
We know these ripples are created when two incredibly massive, dense objects, like two stellar mass black holes, find themselves locked in a binary system. Over time, their orbit degrades, they spiral closer and closer together, and eventually they violently crash into each other and merge, releasing a shockwave of energy that warps reality itself.
And LIGO detects the end of the story, the final fraction of a second, when the merger actually occurs. But the prevailing mystery in gravitational wave astronomy has been understanding the beginning of the story.
Where do they come from?
Exactly. Where do these merging black hole binaries actually come from? Space is vast and empty. How do two isolated black holes find each other and get close enough to eventually merge?
And the musical chairs happening in Omega Centauri provides the origin story.
It provides observational proof for a major formation channel. The dense cores of globular clusters operate as dedicated assembly lines for black hole binaries. Because the environment is so densely packed, the black holes that sink to the core via dynamical friction are forced to interact. They undergo those three-body exchanges, stealing companions and forming binaries.
But oMEGACat BH2 is in a 94-year orbit. That's incredibly wide. Two objects that far apart are never going to spiral in and crash into each other, are they?
Well, a wide binary won't merge on its own. But in the cluster core, the interactions don't stop after the first partner swap. The newly formed binary will inevitably encounter other stars and black holes.
Oh, right. The mosh pit doesn't stop.
Right. Each time a third body interacts with a black hole binary, the physics of the encounter tends to extract orbital energy from the binary, transferring it to the passing star, which gets kicked away at high speed.
So the passing star acts like a brake. It steals orbital energy from the two black holes. And when an orbit loses energy, the two black holes must fall closer together. The orbit tightens.
Through a long series of these repeated gravitational encounters, a process called dynamical hardening, the black holes are forced into tighter and tighter orbit.
Until they merge.
Eventually, they get so close that they begin to emit gravitational waves, which bleed off the remaining orbital energy until they spiral in and merge. The discovery of oMEGACat BH2 proves that the initial step of this assembly line, the dynamic formation of the binary itself, is actively happening.
Finding this one fragile system gives physicists a local, observable laboratory. We can study the exact physical environment that produces the massive explosions LIGO is picking up from billions of light years away.
It allows theorists to really refine their models. Dynamically assembled binaries in dense clusters have different spin alignments and mass ratios than binary stars that simply lived and died together in the empty suburbs of a galaxy. Understanding the Omega Centauri factory helps us decode the history of the black holes crashing together on the edge of the observable universe.
But the implications don't stop with gravitational waves. Let's look inward at the cluster itself. If the mathematical models are right, and Omega Centauri really does harbor a swarm of up to 10,000 black holes in its core, how does that invisible swarm affect the millions of normal glowing stars trying to exist around them?
The black hole swarm completely dictates the structural evolution and the physical shape of the cluster over billions of years. To understand how, we have to look at the concept of kinetic heating.
Kinetic heating. So we aren't talking about thermal heat, like fire. Black holes don't emit thermal radiation.
No, we are talking about the energy of motion. Gravity is an attractive force. It always wants to pull mass together. Left to its own devices, the combined gravity of 10 million stars in Omega Centauri should pull the entire cluster inward.
Okay.
The stars should fall toward the center, causing the core to become denser and denser until it undergoes a catastrophic process called core collapse, shrinking into an infinitely tight point.
So gravity's constantly trying to crush the cluster into a ball. What is stopping it? Why hasn't it collapsed after 12 billion years?
The hidden black holes are stopping it. Remember the dynamical hardening we just discussed?
Yeah.
When a passing normal star interacts with a heavy binary system in the core, the star steals energy and gets kicked away at high speed.
Oh, the black holes act like gravitational slingshots. They impart tremendous momentum to the lighter normal stars, physically launching them outward away from the core.
That outward scattering of stars creates a constant kinetic pressure that fights against the inward pull of gravity. It literally puffs the core up, inflating it and preventing the cluster from collapsing.
It is amazing.
The swarm of invisible black holes acts as the structural scaffolding holding the entire stellar metropolis open. Without them, the shape and density of Omega Centauri would look completely different today.
The invisible monsters lurking in the dark are actually the architects keeping the entire city from collapsing into ruin. The physics of that balance is stunning. And this scaffolding concept actually ties directly into what might be the most intensely debated topic surrounding Omega Centauri: the hunt for an intermediate mass black hole.
Oh, yes. The search for intermediate mass black holes is one of the most pressing mandates in modern astronomy.
Because it's the missing link, right?
Exactly. We have abundant evidence for stellar mass black holes, like the 4.5 solar mass object we've been discussing. And we have undeniable proof of supermassive black holes, which weigh millions or billions of solar masses and reside at the centers of galaxies, including our own.
But there is a massive missing link in the evolutionary chain. How do you get from a tiny stellar mass black hole to a galactic behemoth? There has to be a middle ground, black holes that weigh tens of thousands of times the mass of the sun, but we struggle to find them.
They are the crucial stepping stones required to explain how supermassive black holes managed to grow so massive so quickly in the early universe. For roughly 2 decades, astronomers have been analyzing the movement of stars in the very center of Omega Centauri.
Right, trying to find one of these intermediate ones.
Yes, some teams have claimed that the extreme velocity of those central stars proves they are orbiting a single, massive point of gravity, an intermediate mass black hole weighing roughly 40,000 solar masses.
A single giant monster sitting exactly at the core. But other teams look at the exact same data and say, no, it's not one giant black hole, it's a swarm of thousands of small ones.
The debate has been fierce because the gravitational signatures can look nearly identical. A diffuse swarm of thousands of stellar mass black holes can collectively mimic the gravitational pull of one single intermediate mass black hole located at the center.
Ah, I see.
If you cannot resolve the individual members of the swarm, you cannot definitively prove the giant monster exists.
The swarm basically masks the presence or absence of the bigger black hole.
Exactly the problem. You cannot confidently claim to have discovered an intermediate mass black hole until you have completely mapped, modeled, and accounted for the gravitational influence of the stellar mass black hole population surrounding it. The discovery of oMEGACat BH2 is not just a neat find, it is a mandatory prerequisite.
Wow. Finding this one quiet, 4.5 solar mass black hole is the first tangible step toward mapping the swarm. Once we map the whole swarm, we can subtract its gravity from the equation. If there is still a massive gravitational pull left over, then we know the giant monster is real.
By identifying the individual components of the central dark mass, we are systematically unlocking the door to solving one of the most significant cosmological mysteries of our time.
When you step back and look at the sheer scale of the physics we've discussed, from quantum degeneracy pressure failing to violent musical chairs to gravitational waves rippling across the universe, the thing that resonates the most isn't just the math, it is the philosophy of how the discovery was actually made.
It's a great story.
It is. We live in an era of massive, multi-billion-dollar telescopes launching constantly, but this paradigm-shifting breakthrough didn't come from a new machine taking a new picture.
It is a profound testament to the scientific method and the enduring value of archival data.
The Hubble Space Telescope collected the images used to track this microscopic astrometric warble over the course of 3 decades. But the astronomers who took those original pictures in the 1990s and 2000s weren't looking for black holes, were they?
Not at all. They were studying the variable brightness of stars, mapping the different chemical populations we talked about, looking at how the cluster as a whole rotated. They took the pictures, did their research, and stored the data on hard drives.
The information was recorded, captured in the subtle alignment of pixels year after year. The secret of the orbital wobble was sitting there, fully documented, just waiting for the technological and analytical capacity to catch up.
Yes, it required a new generation of scientists armed with hyper-precise astrometric algorithms and the computational power to track subpixel variations across thousands of images to finally ask the old data a completely new question.
It is the ultimate exercise in human patience, gathering the light, storing it, and trusting that one day someone with a different perspective would be able to see what was hidden right in plain sight. And then seamlessly integrating that historical baseline with the cutting-edge infrared precision of the James Webb Space Telescope to provide the final, decisive confirmation.
The methodology highlights the complementary nature of astronomical observation. In a discipline currently dominated by massive, rapid sky surveys designed to catalog millions of transient events every night, the discovery of oMEGACat BH2 serves as a powerful reminder.
That there's value in just staring.
Exactly. There is still immense, world-changing scientific value in simply staring at the exact same spot in the sky with incredible care for a very long time.
So as we wrap up this exploration, let's take a quick look back at the sheer distance we've covered today. We started our journey in the southern hemisphere, zooming into a chaotic, ancient stellar city packed with 10 million stars, a city that the kinematic and chemical evidence suggests is actually the stripped, dead core of a cannibalized dwarf galaxy.
We examined the mathematical certainty that roughly 10,000 black holes should be sinking into the core due to dynamical friction, and how the complete lack of interstellar gas rendered them utterly silent to our X-ray observatories, while extreme crowding blinded our radial velocity measurements.
We broke down the monumental engineering feat of high-precision astrometry, tracking a star's physical side-to-side movement across a digital sensor by fractions of a pixel over 20 years, until we caught the tiny 94-year corkscrew wobble of a normal star being violently dragged off course.
We analyzed the anomaly of a 4.5 solar mass black hole, an object too heavy to be supported by neutron degeneracy pressure, yet surprisingly light for an ancient, metal-poor environment where weak stellar winds should have left behind massive stellar remnants.
And we discovered that this bizarre, fragile, wide binary system cannot possibly be 12 billion years old. It is the direct result of a violent cosmic mosh pit, a chaotic environment where three-body interactions forced black holes to steal partners, actively assembling the very binary systems that will eventually spiral together and send gravitational waves washing over our own planet.
The scientific trajectory moving forward is steep. This single, quiet detection in Omega Centauri is not an isolated event, it is a proof of concept. The astronomical community is on the verge of deploying next-generation observatories. Instruments like the Nancy Grace Roman Space Telescope will provide Hubble-level resolution, but with a massive field of view, while the extremely large telescope currently under construction will offer unprecedented light-gathering capabilities from the ground.
We are going to take the astrometric tracking algorithms that took 20 years to perfect on this one star and apply them to millions of stars simultaneously. The trickle of data is going to turn into a flood.
We will transition from analyzing single anomalies to comprehensively mapping the hidden populations of quiescent black holes across the entire Milky Way and beyond. This will allow physicists to rigorously test and refine our overarching models of mass distribution, dynamical cluster evolution, and the formation pathways of gravitational wave sources.
It alters your perspective on the night sky. It makes you realize how much of the universe is still waiting to be uncovered, not necessarily by building a bigger rocket or looking further out into the void, but simply by looking much closer at the light we have already captured.
Beautifully said.
And that brings me to a final thought I want to leave you with. We just spent this time breaking down how a paradigm-shifting black hole, a discovery that forces us to rewrite stellar evolution and orbital dynamics, was hiding quietly in a server rack full of 30-year-old telescope pictures. It was patiently waiting for the right software and the right curious mind to reveal its presence.
Just waiting.
So it makes you wonder what other fundamental truth about the physical laws of our universe, what other seemingly impossible discoveries are already sitting on hard drives right now, silently waiting for you to ask the data the right question.